All sorts of things can go wrong when you're taking force curves. The cantilever can slide along the surface. The scanner can have hysteresis. The end of the cantilever can nod up and down if there's friction and you're working on a compliant sample. You can do the calibration badly, and the photodiode can saturate. What do those all look like? Some quick sketches for you here. As alluded to at the end of lesson 21, the cantilever is often at a slight angle, different from horizontal in AFM. That's because a typical tip is only 10 to 20 microns, 5 to 20 microns in height, and it's difficult to get the cantilever and sample perfectly parallel with such short tips. So that's why most AFM cantilevers have 10 to 15 degree angle of repose. Another consequence of that, besides just the fact that the force is not normal to the surface, is that when you bring the scanner down towards the sample, well, the cantilever length doesn't change, and so that means you slide along the surface of the sample. So instead of leaving a hole, you leave a scratch, and depending on the materials and the experiment you're doing, that might or might not be a problem. But it's good to check after you have done a strong force curve to see if you've left a hole or a scratch. If you have to indent with large forces, you might not find AFM is really the best tool. You might want to go for a class of instruments known as scanning indenters. They are kind of a cross between AFM and depth sensing indenters or nano indenters. Scanning indenters have a diamond tip that's normal to the surface. They don't have quite the force resolution of AFM. They don't have quite the lateral resolution of AFM, but they do image, and the indentation data are much better. And as an estimate to how much your tip will slide along the surface, it can be shown for typical geometries that sliding distance is equal to the change in the height of the scanner times the tangent of the angle of repose. Here's an unusual shape. It tells you that as you are unloading, you have higher force than when you're loading. Clearly that is unphysical, and it indicates hysteresis in your scanner, and you better look into that. A similar shape would be like this, loading, then kind of a hiccup here, and then a steeper slope on the way out. What this is indenting a very compliant sample, and friction is causing the end of the cantilever to nod up and down as it slides along the surface of the compliant sample. This might happen, for example, when you are trying to calibrate a cantilever by pushing it against another cantilever of known stiffness. Here's another odd plot. This one is telling you that as the force is increased, the material, the sample, is pushing the tip out of the material, and that's not physical. So what happened there? Well, initially during the calibration process, most manufacturers will have you look at a photodiode voltage as a function of scanner height curve. And let's say this one looks like this. And this will be on a rigid material, and in the upper reaches of the curve here, where the tip is in firm contact with the rigid material, we can assume that the amount of voltage you're getting is related to the amount that the scanner has moved, and that the sample doesn't compress at all. So you would get a straight line like this. If instead you're a little bit off and you include some of the lower reaches of the curve, then the computer thinks that this slope corresponds to a rigid sample, whereas in the lower reaches of the curve, well, there you just see from the fact that the slope is changing that there is not firm contact with the sample. So this is the origin of the problem on the left. Occasionally people will show me some raw data that look like this, where there's a very large hysteresis loop and there's a flat spot upon pull-off, and they ask me to help them interpret that. Well, here's my interpretation. That spot corresponds to the saturation of your photodiode. In other words, the cantilever is so weak, it's bent so much, that the photodiode can no longer track it. Some people respond by saying, oh, well, I'm just going to say that what's happening in that area I can't read is I'm just going to extend the line of that force curve backwards. Well, I think that's a bad idea, because yes, many times it is straight and straight back, but there are occasions where the curves look more like that. So I think you should be cautious and just buy yourself a slightly stiffer cantilever such that it doesn't bend so much upon retraction. Another thing that can happen during the approach, even well before you get to the sample, you can see some waves here. What that's from is from having a laser, and yes, most of the laser light comes down, hits the cantilever, and goes to the photodiode, but there is typically some laser light that doesn't hit the cantilever, bounces off the surface, comes back to the photodiode, and there's a path difference between those two beams, and as the cantilever goes up and down, there's interference between those two beams, and that's what you're seeing in this part of the curve. Some manufacturers use modulation to make that less of a problem. Others have gone to superluminescent diodes, which are less coherent than lasers, again, to minimize that. It's particularly bothersome when you're trying to measure small forces. So in this lesson, I just gave you some things to be careful about, attentive to, as you're taking force curve data.